no exactly normal. Trust me, this is gonna be extremely fun. Okay, like the process of like researching for this talk feels quite literally like chasing a cat down a rabbit hole. Like I could never imagine, something this tiny could fit into this many, wonderfully complex details. But so yeah, let's get started. Um, so you guys have, hopefully have heard of or seen the fact that cats can flip themselves 180 degrees while falling in midair. And it's not just cats, right? Many small mammals like dogs, rabbits, squirrels, they all display this ability, this sort of, quite frankly, amazing ability. And to see why this motion is so interesting, let's recall conservation of momentum from PHY1 Physics 151. Okay, so like back in first year, we learned that angular momentum of a rigid body is constant when there are no external torques acting on it, right? So if the cat starts out with zero angular momentum, its angular speed will always be zero, so it can't possibly rotate. So cats break laws of physics each time it flips. As much as we would all love to believe that our pets are secretly physics-defying creatures from like another dimension or something, there's a serious flaw to this argument, which is that cats are not rigid bodies, right? Like clearly, proof by image, no more explanation required, right? In fact, it does not even make sense to assign a single angular velocity to the cat because different parts of it will be rotating about different axes at different rates. So hopefully by now I've convinced you that this is a cruel problem worthy of your attention. I mean, it certainly got the attention of James T. Clerk Maxwell, who was very interested in this problem. In fact, he at Cambridge he kind of developed this like evil reputation of throwing cats off balconies because of this, right? So at the end of the 19th century, there are many early efforts for explaining this motion, right? And some of them, some of the early explanation for this motion includes, okay, maybe the tail of the cat is rotating in the opposite direction to, I guess it's counter rotating in the opposite direction to counter react the angular momentum caused by the rotation of the rest of the body, which this explanation turns out to be not correct since we've also observed, cats with missing tails also being able to flip themselves in midair. So in order to truly understand this motion, we need to fast forward to 1969 and move across the Atlantic to the US. Okay, so 1969, as you guys probably know, was the height of the Apollo era, right? I mean, Neil Armstrong and Buzz Aldrin just walked on the moon, and the NASA was absolutely bloated with money compared to what they have nowadays. So, a couple of people at NASA were like, what do we do with all of this money? How about we solve the falling cat problem? If we can solve this, then maybe we can, teach our astronaut to repeat the same motion in space and, make their life easier and whatnot. So they hired two homeless mathematicians. I mean, just kidding. They actually got like a professor from Stanford to do this. So they gave that professor what's the equivalent of 500,000 USD in today's money to essentially solve the falling cat problem. And that professor's name is Kane. And, that's exactly what he did. He developed a dynamical model for the falling cat that explained the motion. And he was able to essentially teach how to replicate that motion to a gymnast, which resulted in the picture on the right there, where you have the guy on the right wearing an astronaut suit is actually a gymnast. This is not in space. This is shot on Earth. He was jumping up and down on the trampoline, and then he's able to flip himself in midair. Right. So there's that. Okay, so for the I guess first half of the presentation, I am not going to summarize what King did because the way he solved the problem is extremely convoluted and quite frankly just makes no sense. So we're going to go through a more modern treatment of the problem that sort of like streamlined the process a little bit. Okay. Okay. So I've mentioned previously that we cannot model the cat with a single rigid body. So let's approximate the cat with two rigid bodies. Okay. So basically, if you like squint hard enough and like maybe ignore a couple of legs here and there, a cat is nothing but two cylinders attached to each other. Right. Okay. So and this is known as the cylindrical cat. Okay, so the first question is, as many of you who are taking 354 right now knows, is how many degrees of freedom does this system have? Okay, so let's answer that. So from 354, we know that a rigid body has 6 degrees of freedom, right? 3 for translation, 3 for rotation. We have 2 rigid bodies here, so that means that this system has at most 12 degrees of freedom. Now let's turn off gravity, right? So the center of mass of the system is fixed, which that reduces the degree of freedom by 3. And so we're left with 9. Now, there's the condition that these 2 rigid bodies must be attached to each other, right? So that, we don't have one part of the body on Mars and then the other on Jupiter or something, right? So that actually gets rid of 3 more degrees of freedom. So in fact, this system only has 6 degrees of freedom. In other words, it is the state of the system is completely determined by the orientations of the 2 cylinders. Okay. Okay, so step 2 would be to come up with a generalized coordinate for our systems. Generalized coordinates for our systems, right? I've copied that graph on the blackboard because we're going to be referring to be referring to this graph a lot throughout the presentation. So whenever in this talk, whenever you see a symbol that you're like, wait, what does that symbol mean again? Just check here. It's probably out here. Okay, cool. So right, generalized coordinates. Let's define the unit vector A1 to be pointing along the axis of the cylinder, of the front cylinder, and B1 to be the unit vector pointing along the axis of the back cylinder. Right. Okay. And then let's define the vector C1 as A1 plus D1 renormalized. Sorry, I mean normalized. And C2 as A1 minus D1 normalized, and C3 as C1 cross C2. So together C1, C2, C3 makes a orthonormal frame, right? And of course, if you can imagine these cylinders rotating in some weird ways, all of these vectors are time dependent, right? Okay, so let's continue. We're going to define the angle phi as the angle between C1 and B1. Okay, it is equal to the angle between A1 and C1, clearly. Right, and then we're going to define theta f as the angle between, say, the front leg of the cat with respect to some fixed axis. Right. So theta f parameterizes the rotation of the front cylinder about A1. And similarly, theta b, which B stands for back, parameterizes the rotation of the back cylinder about B1. Okay, so I know I've just thrown a lot of symbols at you, so are there any questions, comments, concerns? There should be lots of concerns. Yeah, go ahead. Yeah. Yep. Yeah. So that kind of leads to concern number 1. So over here in this region, we clearly see the 2 cylinders are physically overlapping, right? Which is not possible. A more accurate model would be to consider these 2 cylinders are actually attached to a sphere, so that they can still rotate around, but also they're separated a little bit, so that there's a bit of room to wiggle without them overlapping like this, right? But in that case, we'll introduce another another constant r, the radius of the sphere, and then that's just gonna, to be honest, clutter the equations way too much. You're gonna see later the equations in this talk are already way too cluttered, in my opinion. So simplicity leads to better understanding. So simplicity. Okay, cool. So that's that. All right. Maybe just let me say make another remark. So you can think of the variables phi, theta, back and theta f as parameterizing the shape of the cat. Okay, and the orthonormal frame, the ci, c1, c2, and c3 as parameterizing the overall orientation of the cat. Okay, and I forgot to write it down here, but later on you're going to see me write matrix C of t. This is just C1, C2, C3 concatenated together to form a matrix. This is an orthonormal matrix. Yeah. Okay. All right. So we're going to assume that the cat can change theta b, theta f, and psi to be whatever smooth function it wants. Okay. As long as those functions are satisfies the conservation of angular momentum. Okay. So well actually I'm gonna add a condition to this. Thetas and phis can be whatever function the cat wants within reason. We probably don't want our cat to go relativistic. And in fact, you know what? Thinking about it now, unless you fancy like a supersonic boombox living in your house, you probably don't want it to go supersonic either, right? So, yeah, side remark. Anyways, so our goal, right, is to find the functions theta of t, phi of t, and c of t, such that the angular momentum is always zero for any t, and we want essentially we want c to flip itself 180 degrees about c2, right? So basically that means that we want c1 of 0 to be equal to negative c1 of t for some fixed end time capital T. And similarly, c3 should be equal to negative c3 of t. So that's the 180-degree flip. And we also want all derivatives of our dynamical variables to be 0 at t equals to 0 and t equals to t, right? So we want our cat to start not moving and end not moving. Okay. So I guess it's worth pointing out that we're not trying to find the equations of motion for this system, right? Because the equation of motion just tells us the cat starts at rest and therefore will remain at rest forever, right? What we're hoping might happen is that through some clever choices of the functions theta and phi, if we plug that quote unquote clever choice into the conservation of angular momentum, we may force C to essentially flip 180 degrees. Okay, so that's our hope, and we'll see soon enough whether that hope is justified or not. Okay, so I guess so back here, I said that the angular momentum is dependent on theta f, theta b. Like the angular momentum is obviously dependent on all of our dynamical variables and their derivatives, right? But the actual functions that labels that dependence is is kind of complicated to arrive in the sense that it takes a lot of linear algebra and then trigonometry and then looking at diagrams, chasing stuff in order to express m of t, the angular momentum, in terms of our dynamical variables. So which is why I'm going to skip that step and just straight up show you what m of t equals to 0 looks like. However, there is one, I guess, key part of that computation that I do want to highlight, which is that this matrix C diagonalizes the sum of the moment of inertia of the two cylinders. I guess, recall from physics 354, I guess you guys have probably seen this like this Wednesday, right? That the moment of inertia is a rank 2 tensor. And for most cases, you guys can think of it as essentially a 3x3 matrix, right? And matrices, they are diagonalizable. And my claim is just that this matrix C diagonalizes the matrix IF plus IB, where IF is the moment of inertia of the front cylinder, and IB is the moment of inertia of the back cylinder. Okay, that's all of I'm claiming, and this is why we chose these variables as our generalized coordinates, because they simplify our computations by a lot. Okay, cool. So as promised, we're skipping that crap ton of algebra in there to arrive at that monstrosity on the top right hand. I guess the first thing to say is don't panic. I should explain to you guys what omega of C is, okay? So omega of C is the instantaneous axis of rotation. Instantaneous axis of rotation of the frame C. Okay, so say this is these my fingers represent C1, C2, and C3, right? They are always 90 degrees apart. They form they are always on orthonormal basis, right? So if omega C points upward, then the resulting motion will look something like this. Sorry, the resulting motion will look something like this, right? If omega C is pointing towards you, then the resulting motion of the CIs will look like that, and so on and so forth. And then like above some random, I guess, vector, it's going to look something like this. Well, anyways, you get the point, right? Okay, so that's what omega C is. And as some of you will see next week in 354, the instantaneous axis rotation is usually time dependent, which I guess causes a motion that is very, very difficult to visualize. But that's okay. Trusting Michael Luke, he's gonna make sure you guys understand. Okay, but we are moving on. Okay. Right. So essentially, any motion that satisfies the conservation of angular momentum must obey that vector equation. Right. Okay. So, and this is where the clever choice for theta comes in. We're going to set theta ff to be negative theta v for all time. Okay. So I said it's a weird decision on the slide over there. However, from a perspective of safety, it really isn't that weird of a decision. To see why, just imagine this state where theta f and theta b are both positive pi over 2. Sorry, I suppose I could, try to replicate what that state might be using my body, but unfortunately, in this case, that's not possible because that will require me to break my own back. Right?
Would that be the two parts twisting in opposite direction?
Exactly. Yes. Yeah, exactly. Yeah.
So the cat just die.
Yeah, exactly. Yeah, exactly. My point is, right, for a cat, for any vertebrate for that matter, theta f is always close to negative theta b. Right? Okay, so that's why, this decision really isn't that weird of a decision to make. Okay, so now that we've established that, let's take a look at where that decision gets us, right? So I guess we plug in theta equals to negative theta e to the top component over here to see that it is 0. Just get left with that equation. And from that equation, it is very easy to see that C2 is a constant vector. So basically, in the paper that I got this from, they pretty much just stated that fact and then immediately moved on, like it's the most obvious thing ever. Unfortunately, my brain is like a bit too tiny to see why that's obvious. So like I had to write stuff down in order to see it. Oh my. Yeah, I know. What is that? So on the left-hand side, we have C transpose, sorry. And C transpose is, look at our definition for C over here. If we transpose that, we get that C1 transpose, C2 transpose, C2 transpose, right? That's C transpose. And then omega of C, well, that's a vector. It's the instantaneous axis rotation, but it's still a vector, right? So we can write it as a linear combination of the CIs. Right, since the CIs form a orthogonal basis, we can always do this. And now it just becomes vector matrix multiplication, right? So the first component of this vector is just omega 1 C1, which is this thing, dot product with C1 hat transpose, right? So we just get C1 transpose dot product C1 times omega 1. And then the rest of the terms are 0 because C2, C1 is C1 is orthogonal to C2 and C3. Okay. And then similarly, the second component is omega 2 times C2 dot C2. And then the third term is omega 3 times C3 dot C3. Okay, so this is the left-hand side of that equation, right? Now the right-hand side, well, we have 0 on the for the first and third components, and then something non-zero in the second, right? So this means that omega 1 and omega 3 are both 0, and omega 2 is some non-zero thing that I won't bother writing down. So and now it's time to interpret what this means, right? Recall that omega is the axis of instantaneous rotation. And this is telling us that the only non-zero component of omega c points along the C2 vector, which means that the frame C must always be rotating about the C2 vector in order for conservation of angular momentum to hold. Right? Okay. And this is the moment when we get really, really happy because we've just shown that it is possible for a motion of the cat to rotate about C2 in such a way that that conserves the angular momentum. Okay. So that first equation is just restating of what we just found, right? So we've shown that the cat can achieve a net rotation about C2 essentially by changing its shape, right? And we can find the angle of rotation about C2 by simply taking the time integral of the right-hand side over there, right? Because omega2, remember, is the angular speed of rotation about C2, right? So in order to find the angle of rotation, we just take the integral. And so now our goal becomes to find the scalar functions theta f and psi, such that when you plug theta f and psi into that integral, you get pi essentially. Right. Okay. Cool. And I guess it's kind of obvious that, yeah, it is kind of obvious that there should be multiple choices of, there are multiple choices of theta f and psi that satisfies, that integral equals to pi, right? But we're going to try to compute one of the most simple one, which is just to assume that psi of t is a constant, is some constant that we're going to find, okay? And so in that case, we can essentially just call all of the junk that depends on psi of 0 in our integrals a constant kappa, right? And then we can pull that constant kappa outside of the integral and to get that kappa of psi times the theta f of t minus theta f of 0 should be equal to pi. I mean, fundamental theorem of calculus, pretty simple calculation, right? Right. And I guess in this case, we also want theta f to return to the original position after the cat has rotated pi radians about theta 2 in order for essentially in order for the legs to be beneath the cat as it is trying to land, right? So that's why we also impose the additional constraint that theta f of t minus theta f of 0 should be 2 pi. Okay, and then we just plug everything in, solve for phi, and we get phi equals to pi over 3. And this motion looks something like that. Okay. So I guess a quick explanation for the animation on the left, right? So we can see, the cat is theta f is rotating in some constant angular velocity, and the animation also labels the angular momentum of each cylinder. And you see that the angular momentum of the cylinders as caused by the rotation theta f and theta b can only be cancelled out if the entire cat is rotating in the opposite direction about C2. So this is what I mean by a clever choice of theta f and psi, such that conservation of angular momentum forces the cat to rotate, essentially. Okay. So I guess we're done here, right? I mean, we've solved the problem. We understand why cats can rotate. Back to sleep, not quite. So there are still a lot more, really cool stuff that we can try to understand about this motion. Right? For example, we assume that theta f and psi can be any smooth function that we want, right? So the natural next step would be to ask: is there an optimal choice for theta f and psi that takes "quote unquote" least effort? I'm going to explain what those things in quotations mean later. And also, what about free motion, right? So we're going to define free motion as those that satisfies the Euler-Lagrange equation for this system, right? So if you imagine, the cat is fully relaxed, and then of our dynamical variable starts at some possibly non-zero initial condition, right? So the cat starts out spinning, and then it does nothing to change its shape or anything. It just sits there and let itself spin. That is free motion is about. So in those motions, have angular momentum is obviously still conserved, right? But what about the no twist constraint, right? What about the constraint that was said that theta f will have to be equal to negative theta b? We want to know which free motions still satisfies that constraint. And before we go over the answer to that, I would just like to maybe explain a little bit of why we might care, right? Who cares, right? Because like as you guys have known, for a cat or any vertebrate, its backbone is physically stopping theta f from deviating from negative theta b, right? So for a cat, the answer to that question is never. I'm never going to violate that constraint. I don't want to die, right? So but we still care about the answer to this question, because because if you imagine yourself as an aerospace, like say you're an aerospace engineer, okay, and you're designing a satellite that looks like this with two rigid bodies or whatnot, and let's say you're trying to design the control system for the satellite, right? So and the control system will have to make the satellite execute a maneuver that will require, say, theta f to be equal to negative theta b, right? In that case, it is absolutely vital for you to understand what type of motions, what type of free motions will violate that constraint in order to make important design decisions, such as, I don't know, how powerful does our actuator need to be? Do we need actuators to, enforce this constraint? How much power our actuator is going to draw in order to enforce that constraint, right? Obviously, it's going to be great if no such motions violate this constraint, in which case, your control system just became a lot more easier, and there's basically one less thing you have to worry about in your control algorithm. But this is still a question that is worth answering. Okay, but anyways, that's an aside about engineering stuff. So let's start answering this question by recalling the last question on the first 354 problem set. If you guys remember, you did a whole bunch of index manipulation stuff. And then in the end, you concluded that the Euler-Lagrange equation is the same as geodesic equation for a Lagrangian with purely kinetic term, right? So, when I did that question last year, I was sort of unsatisfied by how little Michael Luke explained what geodesics are in that problem. And so I guess I shall attempt to fill that gap right here. So a geodesic on a manifold a geodesic is a special curve on a manifold. And you don't need to understand why they're special. All you really need to know is that they obey the Euler-Lagrange equation. Okay. So it makes sense. That in order to study the free motion for our system, we should study the geodesics on some manifold, right? And okay, so the answer to our problem, to our question of whether the no twist constraint is violated or not, is essentially summarized by that theorem, which is worded a bit too technically, I feel like. So I'm just going to say the idea behind it, right? So the idea of the theorem is essentially any geodesic that satisfies the no twist constraint at the start will always satisfy it for all time. Okay, this means that any free motion that starts out satisfying the no twist constraint will always satisfy it. Okay, So I guess this is great news for our aerospace engineers because we now have one less thing to control, right? Now, I have a proof for this theorem, which assumes certain knowledge from MAT 363, which I will skip because we're running out of time and I don't feel like many people in this room could benefit from it. So I'm just going to move on to the next thing that I want to talk about, which is there a way for us to optimize this motion, right? Is there, does there exist a certain functions psi and theta such that, the integral of the kinetic energy is minimized? Okay. And as it turns out, the answer to that question, is yes. Okay. And, the phis and thetas that satisfies, that minimizes the kinetic energy expenditure is the solution to the Hamilton's equations for a very special Hamiltonian. I now realize that this sentence probably will make more sense by the end of next month after you guys have seen Hamiltonian mechanics. And I really should have insisted on giving this presentation at a later date, but oh well, the upside is you guys can now, have a sneak peek of what you guys are going to do in 354. So basically, in the last bit of 354, you guys are going to learn the Hamiltonian formulation for classical mechanics. You guys are going to learn what's called the Hamilton's equations, which is a set of first-order differential equations that are completely equivalent to the Euler-Lagrange equations. And since Euler-Lagrange equations, since the solutions to the Euler-Lagrange equations are the stationary points of the action, it is perhaps not surprising that the extremos, the minimizer to this minimization optimization problem is also secretly an Euler-Lagrange equation for some weird special Lagrange. Okay. If that makes sense. And then I've given that special Hamiltonian at the bottom there. Right. And because what's special about that Hamiltonian is that it takes a very similar form to the Hamiltonian of a charged particle. Okay, so I guess down here, this is the Hamiltonian for a charged particle, where Hij is the four vector potential, and then Gij is the metric on the manifold on which the charged particle live. Right? And then if we just compare these two equations, we quickly see that 1 over A in this equation is the same as the diagonal element of the metric G. Okay, so the upshot for all of this is that for a certain special type of geometries, so basically if the cat is composed of two spheres, then we get that this metric is just the normal metric on the sphere, which means that the motion of the falling cat can be mapped one-to-one with the motions of a charged particle on the sphere. So, yeah, funny thing. And that's it. I'll go with Rosanna first.
Models that had been considered. How far through was under model did you get for your last show this?
Well, luckily, I've never considered any model besides this one because I like my sleep schedule and I don't want to waste time on computations. But yeah, there are certainly more accurate models that you can come up with. Mhm.
I
Yeah.
was gonna ask, do you think the table plays like, do you think the process of the table needs to have?
The thing about the tail is that it has very low mass compared to the rest of the cat. So whatever the tail is doing, it can't affect the motion that much.
I mean, yeah, but it's able to. Presumably, it's kind of like the biggest tail situation.
Sorry, what do you mean?
Like the
Like-
first shaper arm. So,
Yeah.
like farther away, it's really, really small.
Oh, I see what you
So it's able to stabilize.
Hmm.
It's like
Oh,
that's the typical purpose of the table. I was like, stabilizes.
Oh, you mean stabilization? Okay, yeah, then sure. I think you can make that argument. But my point is that I think the effect of tail is way too small for the actual flip. I have a question.
Did you or did the guy from Stanford ever publish the tools?
Oh, yeah. He wrote the paper.
I mean, he did. That's the first paper.
Yeah. Go ahead.
Did you also drop cats from balconies to test the theory?
Unfortunately, yeah, I think so.
Oh, wow.
Yeah, go ahead, Larry.
Are cats gauge invariant?
It is. If you choose a very special gauge called the it's in the second paper by Montgomery where he talks about this special gauge that that is essentially the conservation of angular momentum.
Okay.
Yeah. Go ahead.
And then just to confirm, so the model that ends up making sense is like a particle moving over a sphere. That's the kind of form and shape that the cat pursues as it tries to float.
Yeah.
Okay.
Yeah.
The kid showed that video.
Sorry, could you say what?
The kid showed up to like take videos of the experiment they did. That seemed so confusing.
Sorry, I couldn't hear that. They did what?
Like that's like that's what the game shit.
Yeah.
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 Do we have the videos? I don't know.
Oh, I mean, I would imagine that, that picture is essentially frames of the video, right? But I couldn't find any actual videos online. So, yeah.
Yeah.